morning, everyone. My name is Liu Hui. I'm glad to present our work, PriorSplat, Geometry Aligned and Semantic-Guided Unposed 3D Gaussian representations. This work focuses on long-sequence pose-free 3D Gaussian reconstruction from monocular videos. Given only occasionally captured RGB videos, our goal is to jointly estimate camera poses and reconstruct a high-quality 3D Gaussian scene without relying on pre-computed comet poses. I will structure the talk in 3 parts. First, the background and motivation. Second, the PriorSplat method itself. And third, our experimental results and conclusions. 3D Gaussian splitting serves as an impressive 3D map representation for robotic scenes, using explicit Gaussian primitives and differentiable rendering for high-quality normal view synthesis. And now, 3D.js is strong for rendering, but most systems rely on non-poses. Our setting is a long monocular videos without pre-computed poses, requiring during optimization of both poses and Gaussian primitives. In this work, we focus on a more challenging setting, long-sequence pose-free 3D.js. In this setting, both camera motion and scene geometry are uncertain, so the system needs to jointly optimize camera poses and Gaussian primitives. Long-sequence pose-free reconstruction has 2 major bottlenecks. The first one is weak geometric consistency. Existing methods mainly relied on photometric rendering loss. However, photometric supervision only indirectly constrains the 3D structure. As a result, Gaussian primitives may drift away from the real surface, leading to floating artifacts, surface misaligned, and local shape distortion. This second bottleneck is biases the Gaussian allocation. Standard densification is usually triggered by image space gradients or residuals, but image error does not always correspond to semantic or structural importance. Therefore, complex regions may be underrepresented, while simple regions may contain redundant Gaussians. These 2 problems motivate our core ideas. We need external priors to guide where the Gaussians should be placed and where and more the Gaussians are needed. This is the main idea of PriorSplat. We introduce the 2 complementary visual priors into a long-sequence pose-free 3D pipeline, 3D.js pipeline. Master 3R provides geometric priors. It tells us how Gaussians should align with the underlying surface. And Dino V2 provides semantic priors. It tells us where representational capacity should be concentrated. These 2 priors address the 2 bottlenecks I should describe, and they are designed to be complementary, not redundant. Here is the full PriorSplat pipeline. The input is a long monocular video images. We incrementally build the scene, and at each stage, both the geometric alignment module and the semantic allocation module operate in parallel, feeding into the same Gaussian optimizing loop. I will now talk through each module in detail. Let's look at the geometric aligned first. Master 3R is a powerful stereo foundation model that produces dense depth and surface normal estimate. However, raw mask 3R predictions cannot be used directly. They suffered from cross-view inconsistent across the incremental frames, unstable normals near the depth discontinuity, and the scale offset the drift inherent to nomenclature reconstruction. We therefore applied for a four-step refinement strategy. First, scale of the alignment. We use the random depth from the current Gaussian map as a coordinate scale reference to correct the master 3D prediction. Second, depth the edge filtering. We max out the unstable boundary regions where normals are unreliable. Third, confidence filtering. We content only high confidence surface normal estimate. Finally, the survival vex pixel are back project onto a surface cache, which is a set of 3D points with associated with the normals. With the surface cache in hand, we enforce three complementary geometric constraints on each Gaussian primitives. First, the normal consistency. We align with the minimal scale axis of the Gaussian with a local surface normal. This prevents wrong orientations. Second, surface the proximity. We constrain the Gaussian center to remain close to the tangent plane defined by the nearest surface point. This prevents floating. Third, the surface companions. We bound the effective thickness of each Gaussian along the surface normal direction. This prevents excessive volume float. Together, these three losses make the Gaussians behave like a surface-aligned primitives, directly counteracting the geometry inconsistency problem. Now, for the semantic allocation side, standard densification is driven by photometric residuals. This problem is that image error does not correlate with the semantic or structural importance. Importance fine structure may not receive enough Gaussian primitives because they are not dominant source of the rendering loss. So we use the Dino V2 to derive a semantic complementary signal. Specifically, we extract the last layer self-attention map from the Dino V2 to compute a multi-head averaged attention map. After normalization, this gives us a semantic saliency map that reliably highlights the boundary-rich, texture-rich, and semantically silenced regions, exactly the regions that need to more the representation capacity. The signal is integrated in two stages. In the stage 1, during the octree-based initialization, we project 3D points into training views, sample their Dino V2 attention scores, and use the resulting per point semantic scores to bias the octree subdivision, placing more initial Gaussians in the complex regions. In the stage 2, during the training time densification, we project active Gaussians into the current view, sample the local attention, and amplify densification signals in above average attention regions while suppressing below average ones. Clipping keeps the semantic modulation stable, so it as a helper auxiliary rather than overriding the standard gradient-based densification. And we evaluate two standard benchmarks, tanks and table, and free datasets. Our experience use a NVIDIA RTS 4090. We compare against a board of baseline of include of the comet and the 3D dress as a post-upper bond. And the NOP nerve CS 3D dress, no split, any split, instance split, and most importantly, the long split as our primary baseline for the long sequence post-free reconstruction. We report the rendering quality and the post accuracy. This table shows the qualitative comparison with the other methods. PriorSplat achieved better reconstruction quality and post-stability, while keeping good optimization efficiency. This demonstrates the advantage of our method. This slide shows the ablation results. The geometric module improves the surface alignment and post-stability, while the semantic modules improves Gaussian allocation and the detailed reconstruction. The full model performs the best, proving the effectiveness of both the modules. And these quality comparisons confirm this. Across 5 representative scenes, our methods produce visibly clean reconstructions, sharper edges, fewer floaters, and better representation of the geometric details compared to the long split and other baselines. And the semantic visualization on the right further validate the allocation module. Because the semantic salience maps correctly highlight the structural complex regions and the EMA loss, he has showed our methods concentrate the representation capacity precisely where the geometric complexity is highest, matching the semantic prediction with the actual reconstruction difficulty. That's all my presentation. Thank you for your attention. I will be happy to take any questions.
Thank you very much. Are there any questions? No? So I will just start with a question of my own. You were describing your geometric prior, which relied on some kind of depth estimation. How does that work for frames that show the sky? Because there you can't really reliably estimate any depth, right? Is that like covered by your depth refinement step?
Oh, okay. Our refinement mainly including the 3 projects. First, we should in the initialization. We use the master 3 at globe alignment to get initial post and 3D structure and such as and to get as the baseline to start out the project and to make the depth more reliable. So in the tracking period, we use the reconstruction of the current use the current construction of the previous frames to the depth, render depth to as a reference to make all the new added frames to construct the depth more accurate. We use the minimal difference between the reference depth and our new added frame depth to make the minimal depth, so we can make sure the added frames to reconstruct the depths can made more smoothly. And in the third stage, we will make all the project, such as all the 3D points and the poses, to contain a global alignment to optimization. So during the global optimization, we will make the strong constraint to make the depth more reliable. And the most important, because we introduce our ideas, the geometric priors. So during the priors, we made the 3 constraints. First, the normal constraint and the center constraint, and the thickness constraint. The 3 constraints also made the depth more accurate and moderate.
Thank you. Any other questions? No? Then let's thank the speaker again.